probably will not be very difficult. One of the things that I do want to remind you guys, and I don't think many of you guys do this that often, or we haven't had a scenario of it. I've probably told you before, no horizontal math. True. One or two of you guys might solve equations horizontally. Don't do that anymore. We want to make sure we set things up vertically, because what we're doing here with adding and subtracting, all we're doing is combining like terms, guys. Same variables, same exponents, add them or subtract them when you're combining your like terms. Yeah, this is 6-3. So what's happening is in a scenario like this, your book will write it out as a problem horizontally. What I want you to do when you see this is to automatically write it vertically and line up your exponents. Here's what I mean. If I'm reading this out of my book and this is the problem they give me, I put it into a descending order, which I think more often than not they do. And I'm just going to line up where everything goes. Because I'm adding this stuff together, and everything is set up to be combined with the like terms. The x cubed are x cubed, x squared are x squareds. There's nothing under the x because there is one here. So can I do this and it doesn't change it? Oh, sorry, it's supposed to be cubed. And you just line them up, combine like terms. This is something you guys can do in your sleep. And you wind up with that, okay? What you're going to screw up is the subtraction. That's probably what's going to happen. You will screw up the subtraction because the way that they write it is they write it as subtraction of the whole thing. You guys tend to forget to distribute the negative to each of the terms. It is a very, very common thing. Let me show you what I'm talking about. In this next one here, once again, when you go to write it down, don't write it horizontally. Immediately write it vertically and line up where things go. And I'm going to show you how I set these up. It's a little bit different. Go figure. When I do that, everybody agrees that this is a subtraction problem, right? Nope. So I'm subtracting all three of those parts. That's fine. I do it this way because it forces me to make sure that everything gets that distributed part. Yes, sir? Because there's a subtraction symbol there.
There's a secret trick, Mr. McNally.
It's okay. Wait. What's 5 minus 3? 1 minus negative 6.
37.
Negative 7 minus negative 1.
64.
Just watch your signs. What I'm trying to make sure you guys do is not make the dumb mistake by going too fast. Yes, sir.
Can you make it like you add the inverse to every single thing?
If you want, that's fine.
Oh.
Just started. It's only the second example. There's a reason why we have to make sure we remember how to do this. Okay? So take a second and do those two. So, like I said, I just match them up.
I got that one, but I don't get the next one. Where's that 8?
Did you get it wrong?
The last one. I was thinking the 8 went with the right term, but it doesn't.
Once again, I go to the next one. Line them up. As you start lining them up, you'll notice that there's no. But you notice how there's no x value in the top equation? So what's there? 0x. So when you write it out, remember it's going to be 0x minus negative x. Oh, we're subtracting here, so subtract everything.
Oh yeah, I got that.
6x to the 4th. X, oh, sorry. Plus x squared. plus x minus 8.
Yeah.
All right. The worst thing that's going to happen is you're going to say -1 plus 3 is -4. You're going to do something stupid. Don't make silly mistakes. Okay? So here comes the tough stuff.
Oh, wait, I got this. Yeah, I got it.
When you're multiplying, in this case I'm multiplying a binomial to a trinomial, what do you have to do?
A final.
Distribute. We just distribute out twice in this case. Okay? When you're distributing these things, you have to also remember what to do with your exponents. When you're multiplying two things together that have the same base but different exponents, what do you do to the exponents?
N.
You add them. Very good. Okay. So when you set these up, this is nothing more than a distributive property twice in this case, and then combine your like terms.
What is a binomial times a trinomial and is a polynomial?
I don't know. So you distribute out twice, you get 3x cubed minus 2x squared minus 4x minus 9x squared plus 6x plus 12. What?
Hey, can you just like take a moment?
It's distributing, yeah. That's all I'm doing is just distributing. Setting both terms out, okay? Then you combine your like terms. Here's the way that I do it. You always want to put them into a descending order. 3x cubed. I cross it off because there's nothing else to go with it. My next degree is squared, so I underline my two terms that are squared. -2 and -9 is?
-1.
I cross them off because I'm done with them. -4 and 6. And there's my answer.
I got it.
Okay. I usually underline and cross things off. That way I keep track of where I'm at within the simplification of the problem. Does that make sense?
Yeah.
I don't know, you don't need to do it that way. What happens is it just kind of helps you slow yourselves down a little bit so you don't make a dumb mistake. That's all.
I'm really good.
So, do those two. Did anybody do this first one going from right to left?
No.
Yeah, I did.
I would have.
Awesome.
I would have because it's a little bit less. I mean, I wouldn't say it's less work. It's less steps. It's a little bit easier to see. Because what's the property in math that tells you that you can multiply things in any order?
Reflexive.
You did it, yes. What?
See, we had to make flashcards hang for it.
Yeah, we did it back in the day.
I can tell you remember those flashcards? And those were stuff.
Oh, that's all that
I was in plus 6x squared. What?
That's what I got.
Yeah.
This is math.
Yay! Happy math.
I did it.
There's no such thing as happy. I got
Wait,
it.
do you have to do division?
We will. Because isn't division, when you used long division way back in the day,
I used one
What?
for like next way.
where are you going to find money?
Wait, Mr. Murphy, I missed the second one. The answer for it.
I didn't write it down yet.
Oh.
Hey guys, just a refresher. One of the reasons why we spend a minute or two talking about adding, subtracting, multiplying these things is that eventually when we talk about division within polynomials, you go through the same basic steps. You have to add, subtract, and multiply. You don't have to write this down, but just so you remember, when you're doing division, the first thing you'd ask yourself is, does 12 go into 3?
No.
Does 12 go into 37?
Yes.
How many times? 3. So you put a 3 above that, you multiply it out, and then you would subtract. Does 12 go into 12? Once. Okay.
I'm lost.
I'm lost.
Where'd you go?
Where are
How long did you never talk right now?
37 minus 36
Oh,
plus
wait, do you drop it?
Wait,
You drop it.
Guys,
Short division.
we'll get there. 12 goes into 12 once, so 1 times 12 is 12. Subtract out, you get a 0. Drop the 8. Does 12 go into 8?
No.
So you put a 0. 0 times 12 is 0. Subtract it out, you get an 8. Drop the 7. Yes, sir.
Couldn't you just save yourself a step and drop the 7?
You can. I'm just trying to put it. I'm putting it in here for the placeholder. That's all. Okay.
7.
7 times? Because that would be what? 84. Yeah.
Yeah.
So you have a 7 now. So you have 84.
It's 3.
Drop. Thank you.
Yeah.
Drop the 6.
6. 3.
12 goes into 36. How many times? 3. Drop the 4.
It's not going to 4.
12 goes in there is 0. So this would be a 0. And then you have a leftover of 4 over 12. So your answer would be 3. Well, there's no decimals.
No, it's
That's
3, 3, 4, 1.
We usually write more than the 4.
Remainder 4.
R4, yeah, remainder 4, yeah. That's what you were doing back then.
No, we
It's
didn't
the
do
s-
that.
Well, you should. It's the same thing with this.
What was that? 7th grade?
If I'm looking at a polynomial, the only thing it changes now is in order to do this, you want to get rid of your first terms.
Oh, yeah.
How do I turn an x squared into 2x to the 4th? What do you multiply it by?
Square it.
2x squared, right? So since I'm saying x squared, I got to put it above this one, 2x squared.
What?
I multiplied across 3 terms.
Yeah.
Thank God.
Guys, calm down. Relax. You're subtracting out 3 times, just like we were subtracting today. 2 minus 2 is gone. 3 minus negative 4, 7. 0 minus 4. Bring down the 5. How do I turn an x squared into 7x cubed? Multiply by 7x. Subtract out. Negative 4 minus negative 14, 10x squared. 5 minus 14, that's 9x. How do you turn an x squared into a 10x? Oh yeah, drop the 1.
10x.
Times 10. Not 10x, just 10. Subtract out. Negative 9 minus negative 20, 11. Negative 1 minus 20, negative 19. That's your remainder. Oh, sorry, plus 2.
This is the most complicated part of this lesson
Oh, God.
on the board, and it's not going to be on the smart board, so it's not going to be in the video.
Right, but we're not there yet. I'm just showing you the reason why I'm reminding you guys how to do your adding and subtracting and multiplying is that when we get to using this, you have to multiply,
Yeah.
you have to add and subtract, you have to multiply, add and subtract. You're doing the same stuff. Yes, sir?
Why is negative 1 minus 20 negative 19? Isn't it negative 21?
Oh, yeah, sorry. Thank you.
Oh,
I didn't even catch it when I did that.
Sorry, you're right.
I'm sorry, I was writing numbers down. Start out at the beginning of it.
We'll come back to it when we get to it. All I'm looking at here is you want to eliminate that first term. How do you change an x squared into 2x to the 4th? What do you multiply it by?
2x squared.
And you put it above the term that you're multiplying by. That's it. That's your first step. And then it takes off the chain of events because you start dropping out terms each time. That's all. It's a lot easier than you guys give it credit for. It just looks weird. Yes, sir.
You see that third term to the wrong thing. Why'd you pick the fifth number over 0x?
Because I had to put it, see I multiplied by an x squared, I got to put it above the corresponding term in the dividend. Because it's the rule. You would wind up with wrong valid term. You wouldn't have a valid term to subtract. You see what happens if I did it this way? When I multiplied it out to a trinomial, I got a trinomial. So a trinomial minus a trinomial. I just kept everything working with trinomials. I had to have 3 terms to work. Because I had 3 terms back then. Worry about it next
That's why
week.
you made the third term 0. It is 3.
Speaking of three terms, speaking of three terms, in this case, we're multiplying three, you want to call it factored terms. X minus 2, x minus 1, x plus 3. If I set those equal to 0, you could tell me where the graph crosses the x-axis, couldn't you?
Yeah.
2, 1, and -3, right? Well, hold on. I want to FOIL this out. I want to FOIL. FOILing is only for multiplying two of them together. I have to distribute these things. So what I would do is pick any two of them, FOIL them, and then distribute the third.
Okay. Easy.
Okay? A lot of these you should be able to start to do in your head. If I'm looking at this one, if I have x minus 2, x minus 1, if I FOIL that out, you should be able to do that. You get x squared minus 3x plus 2. Then you have to multiply it out to the x plus 3. And in this case, I'm going to work backwards. X cubed minus 3x squared plus 2x plus 3x squared minus 9x plus 6. Three x squareds go out, and I get that. What's happening here is that you're going to be able to look at these things over the course of the next few days and know that if I set that equal to 0, I'd be at 2, 1, and -3 for my values. Do you agree? You also know that it's an x cubed polynomial, so you can tell me what the tails are doing, right? What do the tails look like here? What is it doing?
Oh, it's cute.
It's going up like this, isn't it? So aren't the tails going to be like that? So the tails are dancing. It's going to be here and here, right? So it'd be increasing, then it's got to change direction and go back up.
Oh, I get how that works now.
That's what we're getting to. That's the whole point of knowing those dances, which way things are moving from. Because we're going to be able to do this.
Are we gonna have to do like red equations to make units one?
Eventually. It's not as bad as you think.
This is very hard.
Just by looking at that, difference of squares, right?
I don't know how to do it.
The difference of squares, x squared minus 4. Okay. That's working backwards from that, which we've done. What I want to make sure you guys remember is that the new one. Oh, I don't want to use 3. I want to say x plus 4 cubed. There's a special pattern that works for this every single time. If I have x plus 4 cubed, that means x plus 4, x plus 4, x plus 4. Do you agree? Yes. All right. Well, there's a special pattern that happens here. Do you guys agree that there's an x and a 4? There's two terms here in there? Or two parts. Here's what you're doing. Every time, this will always work. You have an x cubed, because it's the first term, cubed. You're going to have the last term, cubed. Okay. In the middle is where things get weird. Since this is positive, we're going to wind up with 4 terms. Each one of them will be positive. It's always going to be 3x squared, 4 to the first power, plus 3x times 4 squared. Now what I want you to see what happened here. Notice how my powers, my degrees of my x values are descending, while my powers of the 4 are ascending.
That's fancy.
The first term's degrees are descending, while the second term's degrees are ascending. If I put it in there, couldn't I also say that this is 4 to the 0 out here? Because 4 to the 0 is 1. Back here, couldn't I have an x to the 0? Because x is 0 and 1. Yes, ma'am?
Are you using the 3 because the exponent?
No, I'm using the 3 because there's a rule here that happens. What this is called is a binomial expansion. There's a little something in math called the binomial expansion theorem. It's kind of messy, but we actually study it when we get to probability, which is weird that we do that way back then. What that allows you to do is to take higher ordered polynomials and write them out. Because there's a pattern that happens. And it happens with every single one. What's happening here is that if I'm using the binomial expansion, a plus b to the n, it's, oh, what is it? N choose 0, a cubed, a to the n, b to the 0, and so on and so on. This value here is a n choose r. Ever seen those, or permutation combinations? Yeah. It's been a long time, you might not have even heard of it. What's happening here is if you use permutation combinations, in this case it's a combination, binomial expansion, these two numbers just work out to be 3. Because this is a cubed term, it's the second term, and so on. This number equals 3 both times. That's why it works.
So that number 27 on the bottom one right there?
It would be something messier than that. It gets really awful. But it's really easy to use once you learn the theorem. We're not anywhere close to working the theorem. All I'm saying is that this number 3, this number of 3, it just stays constant. It'll always be a 3 for those 2 parts. Okay? So then you just go ahead and simplify it out. You get x cubed plus 12x squared. 16 and 3 is what, 48? So I get that from my expanded form of that after I simplify it. It's just a matter of descending degrees for the x term, ascending degrees for your constant. Okay.
And you use 4 because it was inside the parentheses, or is that also just under
I used the 4 because it was inside the parentheses. This 3 here, this 3 will always be a 3. So if it's x plus 5 cubed, x cubed plus 3 times x squared, 5.
I would prefer to actually boil that out. That's confusing up there.
This is the same, it's faster. It's faster. What's that? Yes, this rule works for cube. No, when it's squared, you.
Oh,
But what about when,
so when it's 5, when it's 5.
see what I was saying about?
Oh,
It's just working out quickly like that. Okay. The idea of understanding the special pattern and how it works is going to help you tremendously when we get to factoring, because the factoring of these things works backwards. Okay. So you have x cubed, 15x squared, 75x, and more 25.
How does it work with the 3x squared to the 4th, to the first power, those kinds? How do you account for those? Because they're like right next to each other, there's no sign or anything.
What are you talking about? For which ones?
Up above the 3x squared, 4 to the first power.
Oh, here?
Yeah, that.
What's 4 to the first?
4.
What's 3 times 4?
12. And
Here, it's 4 squared is 16. 16 times 3 is 48. Okay, I'm just simplifying them into here. That's all. Now, the only other part of this is what happens when it's negative. Okay? What happens when it's negative is the rules don't change. The rules don't change at all. It's still going to equal first term cubed, and then it'll be 3x squared times 6, and then it's going to be 3 times x times 6 squared, and then it's going to be a 6 cubed. Those 4 values don't change. What changes are the signs. So let me ask you this. What's a negative times a negative times a negative? It is alternate. Start at the back end and work your way forward. You won't mess it up then. Because if you think about what you're doing, if you cubed it, if you did FOIL it out, you have -6 times -6, again, you 36. Then you have to FOIL that to another -6. That's why that last term will be negative. So it's much easier to work your way from the back end forward.
Because it's cubed over there and then squared and then.
It works out a little bit like that too. Yep, that's exactly why. This is the -6, this is the -6 squared. So you just simplify it out, you get x cubed minus 18x squared, 72, 108, 216? I think that's 216. Sounds right.
And that's really good.
Everything was like.
Pretty much.
Well, we have the list is that like you did say power.
If it's to the 4th power,
You're trying to tell.
I'm not trying to kill you, but this is a good question. If it's x plus 2 to the 4th, isn't that x plus 2 squared, x plus 2 squared? Wouldn't I just do it this way and just write it as x squared plus 4x plus 4, x squared plus 4x plus 4, and then just FOIL it, or distribute it from there? If you knew binomial expansion theorem, I'd say go for it, because it's really not that difficult to use. It just looks really, really bad. Okay. But yeah, I would just break it into something like that. Okay.
Wait, so don't use that thing with the 3 in it? Is that
Oh,
what-
yes, use the thing with the 3. She was asking me about a 4th degree rule.
Oh, okay, I got
Wait,
you.
are we gonna need that to know that's in the fourth
I
degree
got
thing?
No, there's no pattern to it.
Okay, good.
Okay.
Because I didn't write it down.
Because, or I would have done the x plus 2 cubed, use that pattern, and then multiply it by x plus 2. I do that also. Break it down to x plus.
You saw that tonight.
Hey, what do you call fish? Or fish?
Yes.
So are we gonna have to use the cube like throughout this week or next week?
Yes.
Yes
to both. You're going to want to use it as much as you can. The more you use it, the easier it is. Okay? Here's what I want you to do. Section 6.2. No, 6.3, sorry. Page 341.
Oh, I got it. That was over.
Why did the angry fish search for a new next year?
Why did the angry fish? Angler. What's an angler?
No, that's the one that has like.
Those, please.
Big ass teeth. That's really scary.
No, I'm talking about who's crazy.
Throw yourself off the cliff and then go and divide yourself.
Who wants to have like a study session tonight?
Let's go.
You think I'm gonna get an eye on
Hey, is
it?
anybody drinking tonight? Because I
Those, please, should not take you very long. Like I said, we're going to graph a whole bunch of stuff tomorrow without a calculator.
Would we ever need a calculator?
I don't know, probably 6'4".